So last time we looked at the derivation of double integrals with polar, and we found that the area element for polar is r dr d theta. And that's key when you're setting up any double integrals in polar coordinates. So be a pirate and think r. So we're going to do a new example here. We're going to set up a double integral in rectangular first. And then we'll see why it's a good idea to switch to polar coordinates. Okay, so we're going to find the volume of a solid bounded by this paraboloid, that's the capping surface, and the xy plane. So the xy plane is going to have the base of the solid. Now, if you graph this paraboloid, it's an upside down paraboloid, and it looks like this. So if you can imagine that solid, we're going to find the volume of that solid. Okay, well, from our discussion of volume and double integrals, we know that it's going to be a double integral over a region of integration where the capping surface belongs in the integrand, and then you'll have some area element. So for us, in rectangular coordinates, we've got the capping surface, and then I'm going to choose my favorite order of integration, dy dx, and then what's the region of integration, the r? Well, if you look here, they're not giving us any equations of what's going on in the xy plane. So how do we know how our base is going to roll? Well, you're going to figure out the trace, the intersection of this paraboloid with the xy plane. Well, how do you do that? You set z equal to 0 in the surface equation, the capping surface, and you'll see how it intersects with the xy plane. So in this capping surface, if I set z equal to 0 and then rearrange the equation just a little bit, it looks like I get a circle centered at the origin of radius 2. So in other words, the region of integration looks like this, and that's the base of the solid. That's your R, that's your region of integration, that's the base of your solid. Great. Now, if I'm going to find the limits of x and y here, if I were using my favorite order of integration, dy dx, say, so let's just look at that. That's my favorite. X looks like it's going from the pure number to pure number, -2 to 2. And then y, if you put your little man in there, or representative rectangle or whatever, here's my little man. The man's head is on the upper circle, the upper semicircle, and his feet are on the lower semicircle. So when I solve this circle equation for y, I get two answers. Y will be plus or minus the square root of 4 minus x squared. And that actually, those are going to be my limits. The upper limit is the upper semicircle, and the lower limit is the negative square root of 4 minus x squared. So there. Now I could go ahead and integrate this, but what's going to happen after I do the easy part of just integrating with respect to y, that's going to be simple because I'm just integrating a polynomial there. But after I plug in those limits, I'm going to end up, oh my goodness, probably having to do trig sub and some other horrible things. So I don't want to try to even go there. So what's the fix? The fix is don't. Instead, convert to polar. My goodness. And the reason why this is a perfect candidate for polar is the region of integration is a circle. So anytime you have circles or portions of circles or polar graphs, essentially polar sectors, those are the best type of double integrals to convert to polar. So now what? Well, if you look at this region, what are the limits of r and theta? And there, I claim everybody's going to be a pure number. Like theta is going on the full revolution, 0 to 2 pi, and r is blooming out from 0 to 2. So that's going to be my limits here. And theta is typically always the outermost integral. And so dy dx, my area element, gets replaced with what?
R dr
d theta. Thank you. Yeah, that's the area element for polar. Now, what about this integrand? How do I rewrite that in terms of polar? You could just do the replacements of 4 minus r squared cos squared minus r squared sine squared, and that will work for you. after you clean it up and simplify. But here's something a little bit quicker for you. That's not my way for this particular example, okay? And the reason why is if I factor out a negative from the x squared and y squared terms, I have 4 minus the quantity x squared plus y squared. And does anybody remember the conversion for the sum, x squared plus y squared?
R squared.
Yes, thank you, Nick. Yeah, so there you go. So now this is super easy to integrate. But before you do, please remember to distribute the R from the RD theta before you go on and integrate. Otherwise, you'll end up in a world of hurt and you'll get it wrong, and that'll be sad. Yep. Well, I'm going to have to buy another cooling stand. Man, it's getting pretty expensive doing this online teaching. I just spent over $100 on Amazon for a new microphone, and I don't want to talk about it. Okay, so if I distribute my R, then this is super easy to integrate with respect to R. So I'm going to go, oh, okay. So then I'll have what? 2R squared minus R to the 4th over 4. And those limits, evaluating that, going from 0 to 2. And that's super easy. So you'll just plug in your 2. And I'll end up with what? That's going to give me, what, 8 minus 16 over 4? 8 minus 4? Ah, that's just 4. Since that's just a constant multiple, I'm just going to pull the 4 out of the last integral that's left. Now, how do I integrate this? Is it just 0 or what?
Theta.
Yeah, you understand there's a 1 in there, even though you don't see it. So the antiderivative of 1 with respect to theta is theta. And then you'll evaluate him between 0 and 2 pi, and your final answer will be 8 pi cubic units, and there's your volume. Okay, fantastic. We just found the volume of a paraboloid bounded below by the xy plane. Very cool. Questions?
I'm fine.
Everybody okay? You get that? You're good?
Mm-hmm.
Good? Okay, let's move on then. Let's do something harder. So what if somebody said, okay, well, what if you want to find another volume this time? We're going to find a volume bounded above by a hemisphere. And the hemisphere is the upper hemisphere of a sphere bound, centered at the origin of radius what? Can anybody see what that's going to be?
Radius 4.
Yeah, if you square both sides, just because I want you to see that this is indeed a sphere equation. If you did square both sides and you rearranged the equation, does everybody see it is indeed a sphere equation?
Yeah, I see it.
You learned that back in week 1 in this class, remember? Cool. And so when you solve it for z, which you need to do because that's the capping surface, you'll get plus or minus the square root of 16 minus x squared minus y squared. And we're looking at the upper hemisphere. So we're looking at this upper hemisphere. There's your capping surface. But we're not finding the volume of a half of a sphere. I mean, that we wouldn't even need a double integral for that. We could just use the formula for volume of a sphere and take half of that. So this is the capping surface, but it's bounded below by the circular region R here in the xy plane, which is a circle of radius what? Centered at the origin, but a circle of radius what?
2.
Not 4, but 2. So I keep trying to change colors and I don't seem to be getting it. So here we go. So if you look at the region here, that's the region R. So what's the actual solid that we're finding the volume of? Not that whole hemisphere. We're finding the volume of this. It kind of looks like a can, but it's got a curvy top, basically. I mean, it looks like it would be a can, but it's got the upper part of the sphere, if you will, is your capping surface. Does everybody see that that's your solid?
Yes.
Isn't that cool?
Kind of weird.
It's kind of weird looking, but it's a cool looking solid. And we're going to get his volume. Fantastic. So we know volume is a double integral over a region, and the capping surface goes there. in the integrand. Okay, so for us, I'm going to go, all right, square root of 16 minus x squared minus y squared. And if I did choose dy dx, you know what's going to happen, right? It's going to be like, oh, the region of integration is here in the xy plane, circle centered at the origin of radius 2. So the constants that x would have limits would be -2 to 2. And once again, I'd have those horrible radicals as limits for y. So I could try and integrate this. Good luck. Try to integrate this thing with respect to y. Can you say trig sub? I don't want to. I'm not gonna. I'm gonna convert this to polar. My goodness. I'm not interested in doing any trig sub in this class. So here we go on the region, which is this region here. The R is going to bloom out starting at 0 out to 2. And theta is the full revolution, so 0 to 2 pi. So when you convert to polar, you're going to have all constant limits, which is a lovely thing. And now you got to convert your integrand to polar. And once again, if you factored out the negative from the x squared and y squared terms, you'll see that what is underneath the radical is 16 minus r squared. And what is your area element?
dr theta r.
Okay.
Okay, you got to be a pirate, get into it, people. I want to hear everybody get into this. Arr! Arr!
Arr.
Arr! Everybody, come on. Arr! Be a pirate. Come on.
Arr.
Arg.
Arr!
Avast, it be me. Hand
Yeah, there
over
we
the
go.
keys to the Merchant Federation.
Okay, so now you're all pirates. Congratulations. Okay, does anybody know what rule of integration we can use to evaluate this integral when we're going to integrate with respect to the r?
It's going to be a u sub.
U sub is true. We're going to use it, but that's a
Power
strategy,
rule.
not a rule. Power rule. Good. Power rule. Because I claim this is going to look like the square root of u du as soon as we identify our u and our du. And if you don't identify your u and du when we're doing integration, I won't give you full credit. You got to give me those. Yeah? So if that's missing, I'm just telling you right now, you're going to lose a lot of points from here on out on any of the integration. And I don't want to hear I do it in my head or that, my other professor didn't make me do that or, any of that. I'm gonna. I want to see it. So the u for us is what's under the radical. And of course, the du would be -2r dr. And good news and bad news. The good news is r and dr are already in the integrand. The only thing that we need would be a -2. So I put one in, provided I multiply the front of the integral by its reciprocal, -1/2. And now, knowing what we know about the power rule here, this is going to be what? 2/3 u to the 3/2. So this is going to help us over here. And so we're going to use that. We're still going to have this -1/2. We still have the outermost integral. And then when we plug our u back in, which was 16 minus r squared, and we'll evaluate that between 0 and 2. Now, you got to be real careful here because a lot of times students, when they're real excited or if they're taking a quiz and they're very fragile and not thinking clearly, they go, oh, for the limit of 0, it's 0 automatically. I won't even bother. And that's dangerous. That's true for polynomial integrands, antiderivatives, but not for antiderivatives like this. Can you see that plugging in 0 is definitely not going to give us a 0 result? So I'm going to pull the 2/3 out and multiply the -1/2 with the 2/3 here, and then do this very carefully because it's going to be kind of messy. So you're going to have 16 minus 2 squared, that quantity to the 3/2, which is not going to be pretty, minus 16 minus 0 squared to the 3/2. And then we still have to integrate with respect to theta here, so better not forget. So some scratch over here. What the heck is going on? So this first term is 12 to the 3/2. And I'm just going to kind of leave it because I don't care. Can't seem to get rid of that. 12 to the 3/2. And then this thing is definitely not 0. That's 16 to the 3/2. Yeah. Now, there's a few ways of going about doing this. Like my math lab, you know, I think will let you get away with this, but I'm going to take away 1 point because this term here, you can clean it up because this is square root of 16 cubed, which is 4 cubed, which is what?
64.
Minus 64. Yeah, so that you can do that. Now this, you could clean it up because there is a square root of 12 getting cubed here. And I believe 12 is kind of nice and that it does have a perfect square as a factor. And then you would have like 2 square root of 3 cubed, you know, like that. So you can then go, okay, that's going to be 2 cubed square root of 3 cubed, but then that's going to be 8 times 3 times square root of 3. Okay, that's really going to, if I did clean it up, it would be 24 square root of 3. Fine. Okay. So I don't know if it was number 2 on the quiz or not. Could be. I didn't give you any polar on the quiz, but anyway. So I did give you lots of stuff on the quiz, though. It was definitely a fun ride. I gave you everything and anything. I threw the book at you, right? Integration by parts, arctan rule. It was great. Okay, so this is really just some number, basically. It's, you know, what do we say it was? 24 square root of 3 minus 64. That's just some number. And now we're going to finally integrate with respect to theta. And then this number is going to be multiplied with the negative 1/3. Okay. And that's just going to be theta. And theta is going to go from 0 to 2 pi. So our final answer is going to be negative 2 pi thirds times this number. And by the way, since this is a negative number, this is a negative number, our final answer is indeed positive. If you did punch this up and give an approximate answer, that is, use your calculator, you do get a final answer that is positive, and you would hope so because it's supposed to be representing a volume. And if you're doing a volume problem and you accidentally end up with a negative, something happened. Something happened. Okay, so there's your final answer for that volume. Questions?
That inequality in part C kind of threw me off. It just means the inside of the circle, right?
It's just inside.
Okay.
It's just inside. Yeah, you're just inside the circle when you have an inequality. And so that's, you know, there's your base right there. And because it's less than or equal, it includes the boundary also, right?
Yeah, thank you.
So I'm going to do letter D on the next page, and it's a little bit harder because there's a little more to it, mainly because the region of integration is a little strange, but I like it because it's kind of fun. Okay, so letter D, they're asking us to use a double integral in polar to find another volume. Oh, man. And they want an annular region as the base, and that means a donut. And so the donut is going to be bounded by 2 circles. This circle, x squared plus y squared equals 1, and x squared plus y squared equals 5. And the capping surface, so when they say bounded above, that's your clue. They're giving you a hint. Sometimes you don't get that hint. But this is nice because they're giving you the capping surface right there. Great. So at least we know how to, when we set up the double integral, how to put something in there for the integrand. So that's going to be the capping surface, which is x squared plus y. And they're telling us that the region of integration is bounded by a circle centered at the origin of radius 1. And what about the other circle, the x squared plus y squared equals 5? That's centered at the origin, but what's the radius? Is it 5?
Radical 5.
Square root of 5. Careful. So it's like here's 2. It's a little bigger than 2, but you know, so it's a weird radius. Okay. And so our region of integration is the donut. So that's the base of our solid. Now, well, what's the capping surface look like? Well, that's when you can either go into GeoGebra or you can bring up my, let me get this going here. So here, if I plug in z equals, what is it, x squared plus y, x, where's the caret key? Do I not have a caret key here? Well, looks like I'm going to have to do hand-to-hand combat here. Gotta go to my keyboard. All right, x squared plus y. Not x squared plus y squared, just x squared plus y. Whoa! Wait a minute, where do you go? So there is the surface. Kind of interesting because it does dip below the xy plane. Because y, when y is negative, it can go below. But that's a cool looking surface there. And so that's considered our capping surface. So very interesting. If we switch up the color, nice. Oh, candy color. Oh, okay, pretty. All right, so there's your surface, capping surface. Okay, now what? Well, you don't even want to see how the limits are going to be for this thing. You'd have to chop it up into 4 pieces. You'd have to have like quadrant 1, 2, 3, 4. If you were going to do this in rectangular, and then you would end up, of course, with trig sub, and you don't want to go there. So better we convert to polar right away. So for this region of integration, that's going to be our base of our solid. R is going from what to what, and theta is going from what to what for our limits for this donut. Any guesses for the limits on R?
1 to square root 5.
Mm-hmm. And theta?
0 to 2 pi.
Mm-hmm. 0 to 2 pi. So we got that going. So if we go, all right, put those on there. Now here's the bummer. If this were x squared plus y squared, which it isn't, we could just go, oh, x squared plus y squared is r squared. Cool. But it's x squared plus y. So now you're going to use your conversion formulas where x is r cos theta and y is r sine theta. So x squared is r squared cos squared theta, and y is simply r sine. And then what's this area element? Be a pirate.
R dr theta.
I'm not going to do it.
You got that right. Be a pirate, people. Come on, have some fun.
Aloe, you're the only one not being a pirate.
I am? Or
No.
who you talking to?
That call out.
Grant.
Okay, Nicholas, do you
Professor
have
Rasky's
any,
gonna.
Nicholas Gonzalez, do you have any 1700 sea shanties that you can share with us? Do you have like a link or something?
Do
I actually
it.
have a
Put it in
link.
the chat box so we
I'm
can
not
go
I
gonna-
look
actually have
at
a
it?
link to a sea shanty that I like listen to an unfortunate amount of like times per day.
Oh, okay, yeah.
Fine.
Well, if you're when you post it in the chat box, alert me and I'll bring it out so we can have some fun today. Okay, first up, do not integrate until you have distributed your R. Okay, so you're going to have R cubed cos squared theta plus R squared sine theta. Now you're ready to integrate with respect to R. No problem because, you know, you're going to hold theta constant. So this term, and put the cos squared theta in front, you're going to have R to the 4th over 4. And then this term, put the sine theta in front just so it's easier to read. The antiderivative of R squared is R cubed over 3. And then you're going to evaluate this between 1 and square root of 5, which is not going to be fun because, you know, it's just going to be a little bit kind of messy. Oh, okay. So, Nick, you've got something for us here.
There's a sea shanty for you.
And then David has one also. Okay, so we'll take this one at a time. We'll do one before the finish this problem, one after. Okay, what the heck is this? I want to
It's a
I
YouTube
want
ad.
like sort of the Disney, you know, in Disneyland they have the Pirates of the Caribbean. The
Yes.
Drunken Sailor. Oh, okay.
Oh, come on. It's you've never heard this?
Oh,
I don't
compelling
know.
is your writing
I
by
don't know.
Grammarly. This lecture has been brought to you by Grammarly, the #1 English resource for college students.
You're pretty good at that. Have you practiced?
I thought that was the video. Not even kidding.
I have never. I don't even know Grammarly has like a slogan. They spelled sailor wrong.
They're Irish. Don't pay much attention.
They could use Grammarly.
Oh,
I'm so pumped.
It is in SpongeBob.
man, this is great. One more verse.
Of course you
Okay,
say that, and it goes
dance
into the bridge.
Open dancing, everybody.
Too early for that.
I fully expect like the River Dance Company to come in and, you know, help us out a little bit. Okay, that was fun. Thanks for sharing that, Nick. And David, we'll get to yours right after we do the rest of this problem, okay? I haven't
Our-
Yes, of course.
so when you plug in that upper limit, square root of 5, okay, I'm just telling you right now, it's not going to be pretty. You're going to have, you know, square root of 5 to the 4th, which I think is 5 times 5 or 25. But then this one, square root of 5 cubed, ugh. And then when you plug in the 1, well, that's not too bad, you know, okay. Because, you know, that's, yeah. And so this whole mess is eventually going to get integrated with respect to theta. Okay, so this is 25/4, this is 5 root 5/3, this is 1/4, this is 1/3. I'm going to combine like terms. So how am I intending to do that? Well, I'm going to take these cos squared theta terms, and I have 25/4 over here minus 1/4 over there, but that's 24/4, but that reduces to 6. So there, I just combine those like terms. Now the other like terms, these sine theta guys, the coefficient isn't that cool because you've got 5 square root of 5/3 minus, when I distribute this negative, 1/3. Which unfortunately is not a very nice number, but what the heck, we'll do our best, okay? So this is where we are, and now we're going to integrate with respect to theta. Cool, huh? Now, do you guys remember the power reduction formula?
Not by memory.
No, of course not.
Okay, well, this is going to be on next week's quiz, and it's going to be on midterm 3, probably going to be on midterm 4, and the final. I'm really into the power reduction formula, folks, and I mean like really into it. And if you forgot it from Calc 2, I'm kind of bummed, but let's go over here and talk about it. Because you're going to get it. It's going to be everywhere, okay? If you are trying to integrate an even power of sine or cosine, you have to remember the power reduction formula, because you're not going to use the power rule on that. Don't go, oh, u squared. No, that's not u squared. Instead, you're going to remember that the power reduction formula for sine squared is 1 minus cos of 2 theta over 2. And for cos squared, it's 1 plus cos 2 theta over 2. Does anybody remember this now?
Oh yeah. No.
Yes.
Is it coming back to you?
Yeah.
Yeah, it's going to be on all your quizzes and exams, homework, everything. So this term here, you're going to need the power reduction formula, the cos one. This one, no power reduction needed. You're just going to go, okay, what is the antiderivative of sine theta? Is it plus or minus cos?
Minus.
Minus. So we're going to have that, and we'll evaluate that between 0 and 2 pi in a second. But over here, you're going to first go, oh, I've got to go 1 plus cos 2 theta over 2 and deal with that. I like to pull my fractions out. That way I don't have to deal with trying to integrate a fraction. And then this is just going to be 3, and then theta plus a half sine of 2 theta, like so. And we'll evaluate that from 0 to 2 pi also. Okay? Everybody with me so far?
Yeah.
Okay. It's going to turn out that when you when you deal with this guy, it's, oh boy, this is going to be kind of gross. Yeah. So I claim when you do, like if you just look at what's going to happen here, you're going to have minus cos 2 pi minus a minus cos of 0. Do you see that? And so that's like minus 1 plus 1. Well, what's negative 1 plus 1? 0. So this term here is going to basically cancel. You know, when you evaluate the 2 pi and the 0, it's going to go away. And then I claim the sine of 2 theta term is also going to end up not contributing anything, because I hope you can see when you do the evaluation of sine of 2 times 2 pi, that's sine of 4 pi, that's 0, minus sine of 0, that's sine of 0, that's going to go away. So that's a big fat 0. So who's the only contributing factor here? It's your theta. He's the only guy that's helping out. So you're like, okay, I'll evaluate theta between 0 and 2 pi, and then my final answer is 6 pi, and I get 6 pi cubic units, and we're done. Okay, so that was fun. And what was the point of that one? There was a few points. First of all, donuts. Donuts being very good candidates, good regions for polar. That's one of the things I'd like you to take away from this example. The other takeaway is if you don't have x squared plus y squared, you do have to use those conversion formulas. And the last thing I'd like you to take away is you are required to know about that power reduction formula. It's here. It's not going away. It's going to be on all my quizzes and exams. Okay? So there were 3 things to keep in mind. Now, I think I accidentally skipped a problem back here. So let's check it out. I've got this thing. Oh, you know what? I'm gonna set this one up, but I may not have time to do it because, well, how much time do I have? Oh, no, maybe I will. Okay. I just have so much stuff. We took some time away from lecture last week when I was asked to, oh, hang on, I forgot. We took time away from lecture when I was covering some midterm solutions, and I didn't factor that into my lectures. Okay, so David, you have a YouTube, what do we got here?
I highly recommend that you don't listen to the entire thing.
10
Okay.
hours, David?
10 hours? Wow. Are you serious?
There are math problems in this class that take longer.
Well,
True as that.
You're funny.
Oh, that accordion slaps.
Yeah, okay.
This is how I look, you know, getting my quiz results back and looking at Fat D.
It's got a nice flow to it, doesn't it? Does he ever sing or no?
The lyrics are not necessary, but
Okay, is
the
this on
song
an
is.
infinite loop? Like if I go down here,
It's not
Yeah.
infinite. Like it ends at 10 hours, you know.
This is
like,
taking me back to bowling
Okay.
alley strikeout screens.
wow, that's intense. Okay, nice. Okay, 10 hours. Wow. Yeah, that is a broken for loop. Okay. We'll get to yours in a little bit, okay? Nicholas Gonzalez. All right. For now, I think I'm kind of burned out on the Drunken Sailor theme.
we have to find new sea shanties.
Yeah. Okay. So let's take a look at this, and we'll come back to. So does one problem feel like 10 hours? Come on, guys. That's probably because you didn't do your homework. Now, come on. All right. This is a little bit trickier. The flavor here that I want us to get is I'm not giving you the region by just talking about the region or giving you an equation. I'm going, check out, you know, the limits on the integral. And you should know how to sketch a region of integration just by converting those limits to equations. Do you guys remember how to do that?
Yep.
Mm-hmm. Mm-hmm. So you're going to look at the outermost variable of integration is with respect to y. So y equals 0, y equals -3 are 2 equations that you need to graph. Okay, y equals 0 is just a horizontal line on the x-axis. Y equals -3. Oops, excuse me, I got to do not vertical yet. -3 is here. Okay, there's y equals -3. All right. So I have 2 of the equations. Then what? Ooh, The innermost variable is x, and so we're going to have these two equations to graph. You got to be careful. X equals 0 is the y-axis, but this is the left-hand side of a circle of radius 3 centered at the origin. If I did square both sides and rearrange this equation, I would get x squared plus y squared equals 9. Can you see that if you solve for x, you'll get two possibilities, plus or minus square root of 9 minus y squared? Well, the plus, and you need to know this, the plus would be the right half side of a circle, but the negative is the leftmost semicircle. So we really want this. Now, here's the hard part. Can anybody see what I need to shade in? What is our region of integration? It has to be bounded by all four of these equations, all four of these
The
fences.
slice of the circle in the left or in the third quadrant.
Good, just this right here. Very nice. There's your region R of integration. So if we do convert immediately to polar, what are my limits for R and theta?
Pi halves to 3 pi halves.
Well, pi halves would start up here, but we're starting
Oh,
here, which
so
I
it's
think.
pi to 3 pi halves.
Good. Pi to 3 pi halves, because we just have a little quarter of a circle down there in that third quadrant. What about R?
0 to 3.
Good. Yeah, don't go -3, even though we do have x going to -3. So these are the limits for R and theta. So when we convert immediately, immediately is supposed to be pi to 3 pi halves, and then 0 to 3. We're going to convert to a polar. So the dx dy gets replaced with what? Be a pirate.
Oh, this is the best class ever.
Art. Okay, and then what about this nasty quotient? Well, x squared plus y squared is?
R squared, yeah.
Okay, integrate that. Ooh. You know, we could just quit the class and just look at YouTube videos of pirates for like the rest of the semester. What do you think?
It'll Edward teach us something. Jesus Christ.
And then you guys would just like, man, I want to take this class over again, right? Sure.
Imagine getting interviewed for an engineering job. So, what did you learn in class? Arr.
What would you do with a drunken sailor? You start singing that song, and they escort you out with the security. Hey, security, get this guy out of here.
We learned how to spell sailor incorrectly.
Folks, you do have to multiply your R's together before you integrate, okay? Now, does anybody remember how to integrate this? This is an improper rational function. Calc 2 people?
Long division.
Yes, long division, people. Long division. Okay, so, yeah, you got to do polynomial long division. And, you know, my Calc 2 people, you know, apparently a lot of these apps that they've been cheating from won't do the polynomial long division part. It skips that step and then boom, immediately goes to the result of polynomial long division and then finishes the rest of the thing for you. And I just give them 0 points credit because I know they're using apps and cheating their butts off, and that's not cool. So here we go. Focus your eyeballs on the highest power terms. R squared times R equals R cubed. And then you multiply this R with your entire divisor here. Or your dividend. Yeah. Okay. So then what do you get? 4R, and then subtract. And you're like, oh, well, you know, here we have a 0. So R cubed, take away R cubed, that's 0. But 0 minus 4R is negative 4R. And we're done because that remainder is a polynomial of degree less than the divisor. Now, here's your quotient Q. Here's your remainder R. Those of you who've had me for calculus 2, you know the deal. This is your D divisor. And so when you actually get done with your polynomial long division, I want you to rewrite the result as Q plus R over D. So you're going to go, okay, R plus negative 4R over r squared plus 4. Now you can integrate with respect to r, right? It's doable because this first term is easy peasy. It's just r squared over 2. This term, which rule of integration will you use? Don't say u sub. We
It's a
already
log.
used u sub. But yes, the log rule, because I claim this does look like 1 over u du, and you're going to get ln of u in there. Tell me the u and the du so I can give you credit.
These are r squared plus 4.
Mm-hmm. And
Du
du?
is 2r dr.
Okay, that sounds about right to me. And it looks like, we do have a 4, you know, I can pull the negative 4 out, and then when I put my 2 in, I'll divide out by 2. So it'll look like this, right? And so this is going to give me negative 2 ln of u, and then when I put my u back in, it'll be that. So what I'll have for my antiderivative is r squared over 2 minus 2 ln, and r squared plus 4 is always positive, so we can drop the absolute value. And you're going to evaluate this between 0 and 3. So it's not going to be like nice numbers. It's going to be kind of yee. So then we have to integrate with respect to theta after done with that. So you're going to have 3 squared over 2 minus 2 ln 3 squared plus 4 minus, and then of course 0 is going to make that first term go to 0, but not the logarithm. Be careful. Plugging in 0 to the logarithm, that isn't going to be a 0. What the heck is that going to be? I think I'm going to have like, I got 9 halves minus 2 ln of what, 13? And then minus minus, so that's going to be plus 2 ln of 4. Now, folks, if you want, you can combine those two logarithms together. That's going to be 2 ln of 4/13. That's fine for you to do that. And then now you just have some weird numbers. So I'm going to pull 9 halves minus 2 ln of 4/13 out of the integrand. It's just some weird number. And now I'm going to integrate with respect to theta, but now you just have a 1 there. So you're going to go, okay, I think this is supposed to be a plus, sorry. So that's just going to be theta, basically, and then you'll evaluate theta between pi. Oops, I'm putting the wrong limits on there. Be careful. I think our limits were kind of strange. It was pi to 3 pi halves, and what's 3 pi halves take away pi? Isn't that pi halves? So our final answer is going to be this weird number, 9 halves plus 2 ln 4/13 times pi halves. I know that's a weird number, and it's roughly 3.3657 approximate. Okay, so what was the point, or what's the recap of this problem? Well, the recap was when you are not given the region of integration directly and you're just given an integral, you have to know how to grab or cherry pick off those limits and convert them to equations and graph your region of integration so that it'll make it easier for you to convert to polar and iterate or put the limits on your double integral. And we also had a little bit of fun with polynomial long division. That's always cool. And the log rule. Okay, so we got a little bit of everything in that example. Fine. All right, next up, a pretty hard example. So far, every single polar coordinates double integral that we've done has r having all pure number limits, and so does the theta. And usually you want to keep your theta as having pure number limits, but sometimes r may not be pure numbers. So this next example is going to have us with that. Okay. So so some other people found some other. Nick? What is this one? Is this better? At least it's not 10 hours long, right? Oh, at least a different song. Nice. Okay.
As I was walking down Paradise Street.
Oh, this is great.
Are these real pirates?
Guaranteed.
Let's get, when do they start putting their instruments?
I don't think they need them.
I don't think they do either.
The instruments detract from the camaraderie that this, this collective singing, creates. I'm sure.
All right, I had enough. Okay, guys.
The guy in the front with the guitar, he's not
I
even
think
using
it's
it.
kind of like a drinking song. You know what I mean?
Every
You gotta
sea
be
shanty is a drinking
heavily to
song.
really appreciate it. Okay, so here we go. Here's another really fantabulous problem that I cooked up for you for lecture. Here, when we convert to polar, R is not going to be pure numbers all the way through. So watch closely. Now, first of all, you definitely don't want to try integrating this baby because trigs suck, you know. And then what's the region of integration? Okay, once again, you're going to graph y equals 0, y equals 3. Oops. So that's easy, horizontal line. And then you're going to graph x equals 0, x equals, oh my God, what the heck does that look like? So if you want to figure out how that graph is going to look, well, you could parameterize it, right? You know, y equals t, x equals square root of 3t minus t squared, and go use your graphing calculator in parametric mode, and you'll see what it looks like right now. Or you can use some algebra technique. So the algebra technique I'm going to do to kind of figure out what that is, just so you can see it, so you can see the benefit of some of the, you know, some of the stuff you learned back in the old days, is what happens if I square both sides. Okay, get rid of the radical. And then how about if I get all of the variables on one side and 0 on the other? And can you guys say complete the square?
R.
Yeah, I know, right? You're like, oh man. Well, you don't have to. Like, if we just left it, let's just leave it for now. Let's leave the 3y over there. If I convert this to polar right now, I can go, okay, r squared is equal to 3r sine theta, and I'm going to do something that I'm not really supposed to do mathematically because I could be in jeopardy of dividing by 0, which is a no-no. But let's assume that r isn't equal to 0, and I get r equals sine theta. So this is the time when I want to whip out the graphing calculator. And if you have one, this is a good time. What does that look like? So what is r equal 3 sine theta? So you have polar on your, oh man, this is taking forever. Here we go. So now if my computer bombs out, it's because this SmartView TI takes up like all the memory I have left on this sad Microsoft Surface Pro. It's really, really too bad. So if you get your calculator going, woo, and you go into polar mode, so let's see where that is. So move your cursor down to, oops, I went too far, right? One up and over to polar, and then hit enter to actually choose it, and then second quit out of here. Then hit your y equals, and whatever you got in there, clear it out from whatever. And then instead you're going to go, oh, okay, well, what does 3 sine theta look like? I don't know. And oh, you know what? While I'm in mode, hang on. Yeah, make sure you're in radians, otherwise this won't graph. Okay, I'm in radians. I'm cool. So I'm going to go r equals 3 sine theta. Cool. And I'm just going to hit it. Did I forget my 3? I did. Hang on. 3 sine theta. And let's just hit it. What happens? Oh, I get a cute little circle that is not centered at the origin. Ooh, and that is a red flag. That means your R is not going to be a pure number to a pure number. So that's a little bit tricky. Now, the other issue is going to be, what's your theta doing? Because if you recall, our original, I'm going to quit out of here because this is like going to burn through my memory. The x was only a positive square root of 3y minus y squared. So I claim that that is only going to be the right half right semicircle here, and here's our region of integration like that. So it's going to turn out that you only want theta going from 0 to pi halves. And if you change the window on your, if you still have your graphing calculator and you're following along, go into window and change your theta min and theta max 0 to pi halves, and you'll see this just sketched out. What's R doing? R is going from 0 right there, and then because it's variable, it's not blooming out from the origin. It's going to be 3 sine theta. So when we convert this to polar, it's going to look a little different than what we've been doing, like that. And then square root of x squared plus y squared is square root of r squared. And then dx dy is r dr d theta. And now we can go ahead and integrate. Let's rewrite this, simplifying this. This is going to be r times r, which is r squared. So the antiderivative of r squared is r cubed over 3. And you're going to evaluate r cubed over 3 between the limits of 0 and 3 sine theta. And so that's going to be kind of weird because I'll pull the 1/3 out. You're going to have 3 sine theta cubed. And then when you evaluate it, 0 at 0. But this is going to be 3 cubed sine cubed theta. Okay, Calc 2 time. Does anybody remember how to integrate sine cubed? I'll open it up.
I actually do. Hold on. I still have one of those like 3x5 note cards that I pinned to my like noteboard.
Oh, okay. He's got a 3x5 card. Very cool.
It's stained in coffee and all sorts of lovely residue, I'm
Oh,
sure.
well, that's okay as long as it's still readable. What do you think?
Okay,
You
okay,
separate
here
the
goes.
factors of sine. You get 1 sine squared, which is a trig identity.
Very good.
He be speaking gospel, lads.
Okay, so in other words, you save a sine factor for later, and then you have the other signs which are going to get converted. How?
Sine squared was at 1 plus cosine, or cosine squared theta.
Okay, you're close. What's sine squared? It's 1, not
Minus.
plus.
Oh, minus.
Very good. Does everybody see this? Is this bringing back some bad memories from your Calc 2 days? I'm
Kind of like
sorry.
these actually. These were kind of fun.
If you distribute your sine, yeah, they were kind of fun, weren't they? Then I hope you can see the first term is easy. You know, what is the antiderivative of sine? You know, we all know how to do that. And the second term, you're going to use the power rule where you're going to go, okay, u is cos and du is negative sine, and then you can use this negative right here. I'll change this to plus. Come on, Microsoft Surface Pro, please. There's plus and negative. I'll use it over here. Yeah. And so this is looking like there's a d theta here, but u squared du, but then that's going to be u cubed over 3. So your antiderivative here is going to be sine theta, and then you'll have plus your u cubed, but that's cos cubed theta over 3. And theta is going from 0 to pi halves. Okay, very cool. And oh, I think, hang on a minute, I forgot to integrate sine. Sorry, I didn't do that right. What is the antiderivative of sine? It's not sine.
Negative cos.
Negative cosine.
Thank you, negative cos. Okay, so there's our antiderivative. And so then if you plug in pi halves first, so you got to be careful here, minus cos pi halves plus cos cubed pi halves. Does anybody remember what cos of pi halves is?
0.
So this whole first mess is a big old 0, but we're not going to have everything be 0 here. We'll have minus cos 0 plus cos cubed 0 over 3. And cos of 0 is not 0. What's cos of 0?
1.
I think it's a 1, right?
It's 1.
And then this is a minus minus after distributing that negative. So you're going to have a 1. And then when you distribute this negative, you'll have 1 minus 1/3, I believe, right? Which is 2/3. So then your final answer is 9 times 2/3, which is 18/3, which reduces to 6. And we're done. Score. And so what was the point of that whole problem besides testing you on some of your old Calc 2 powers of trig stuff. Oh, that was kind of fun, We had a variable r. That was the point. And then go hit it. All right, so now let's take a look at, before we hit mass, let's, and by the way, this next problem is definitely going to be like on the midterm. Yeah, I love this kind of problem. You haven't seen this one. This is a new flavor. What's the flavor? Well, the old flavor is you've got a capping surface when you're trying to look at a solid. And it seems like the base of your solid always is like some flat area in the XY plane where Z is equal to 0. That's not how it's always going to be. What if your solid has a capping surface, so it'll still have, some surface up top, but instead of having a base in the XY plane, what if it has an underbelly that's described by some other surface? And this is the problem right here. Check it out. So Z equals x squared plus y squared is the underbelly. That's this paraboloid here, opening upward. And the capping surface, the top of it, is this greenish blue paraboloid going that way. Now, your job is to imagine what the intersection of these two paraboloids looks like. So what I want you to do is focus your eyeballs on the intersection here, which is right in here. So if I only look at the intersection of these two paraboloids, I get a solid that kind of looks like an egg. Very cool. Go find the volume of that. Now, this is similar to what you did in Calc 1. What do you mean? Well, in Calc 1, remember you had some curve, and then you had another curve, and then you were asked to find the area bounded above by one curve, but below by the other curve, and you had to go, oh yeah, area is going to be the taller guy minus the shorter guy. Remember that? Say yes.
Yes.
Yep. So you're going to do a similar thing. Your volume, instead of just the capping surface going in the integrand, you're going to have your integrand is going to be the taller minus the shorter. I'm not kidding you, people, like for reals. So let me do continued on next page. So your integrand is going to be changed up a little bit here. You're going to have a taller minus a shorter. Okay. So what am I saying? So you're going to go area is going to be equal to the taller minus the shorter. Now, the taller guy was the paraboloid facing downward. That was the 8 minus x squared minus y squared. And the shorter was the paraboloid facing upward, if you will. And so that was just z equals x squared plus y squared. Okay, fine. And you've got some area element, and it's over a region. And here's the hard part. What is this region of integration? Because all these other examples that we've been doing had a flat region, flat on the xy plane, and I'm sorry, but this beautiful solid is it just barely grazes the xy plane. Like if you look down here, this dot where it's tangent to the xy plane, oh, does that mean our region is 0? It's just that little vertex down there? No. So here's how you're going to figure it out. Pretend there's a bright sun shining down on your solid. What directly overhead? What would the shadow of this solid be as that it makes on the ground, where the ground is the xy plane?
Circle.
It is going to be a circle, and this circle is called the projection of the solid. This is a projection. You guys remember projections of vectors onto vectors? Say yes.
Yes.
That's going to be on the final. You bet your sweet Bippy. It ain't going away. And if you take Math 254, you got projections all over the wazooby. So you're going to project the solid onto the xy plane. Well, how do we figure out that shadow? This is going to be not too bad, because the fattest portion of the solid is what's being projected. That's going to be pretty much the shadow. And that's exactly where these two surfaces intersect. So the better question is, to get the projection, of the solid onto the XY plane, you're going to ask, what is the intersection of the two surfaces? And it's going to be where z is equal to z. Really? Well, z, the one of them is this 8 minus x squared minus y squared. The other one was z equals x squared plus y squared. Well, what the heck is this? We're getting there. Just bear with me. Let's clean this equation up so it looks something familiar to us. If you add x squared and y squared to both sides of this equation, what happens? Add like terms. Then what? Clean it up a little more. Divide out by 2. After I factor out a 2 from the right-hand side of those two terms. And then doesn't this look like something you can relate to?
Circle radius 2.
Yep, that's your shadow. This is the projection of the solid onto the XY plane. This is the region R of integration. Good news, that's a perfect candidate for polar. Woohoo! So what are you going to do? You're going to determine the limits when it comes to R and theta. And then you are going to convert to polar. Well, how do you do that? Well, if you looked at your taller minus shorter, so you had, I'm going to kind of put in quotes here because I really shouldn't put the X's and Y's back in here. When you looked at this taller minus shorter going on here, let's clean it up a little bit and collect like terms. So if I distribute the negative and then collect like terms, I have 8 minus 2x squared minus 2y squared. And if I factor out a negative 2 from the x squared y squared guys, then I hope you can see that I have 8 minus 2r squared is my integrand. But hold on a minute. What about R? Be a pirate. Don't forget that. So you want to distribute your R before you integrate. And so you're really going to integrate 8r, r minus 2r cubed. That's a cubed right there. And then I'm just going to say et cetera, because I think this is pretty easy to integrate. There's no surprises. There's no power reduction formula or, trig powers. I think you can do this one safely. And you should get 16 pi cubic units. So what's the point? This one had a little different flavor because you're finding the volume of a solid bounded by two surfaces, an upper and a lower surface. So you got to do the taller minus shorter, and then even harder, you got to figure out the region of integration, which is the projection of the solid, the shadow of the solid onto the XY plane. So find the intersection of the fat part. Okay? Questions?
I'm okay.
Okay, so let's do one more polar and then we're going to do mass. Okay, what's the one more polar? Let's do a review of Calc 2. What? Yeah, we're going to do a review of Calc 2. So I know the last week of Calc 2 was probably a big blur for some of us because, we were learning remotely and it was like, But do you remember how to find polar area in Calc 2?
It's not the area of the sector, right?
Yeah, well, it actually is, but they don't tell you that in Calc 2. So the Calc 2 method, and I'll do this on another page because I'm just fresh out of room. I'm just not doing too good on the computer front today. So right here, we'll do it. Here's the review. The area of a polar sector in Calc 2 was if you're given R equals f of theta, of course, and they want to know the area bounded by that polar graph, it was theta going from alpha to beta 1/2 f of theta squared d theta. And if you forgot this formula already from Calc 2, that's okay. The only caveat was R, which is f of theta, cannot go negative. How do I say this better? Let me rephrase this. I misspoke. In order for this formula to work, and this is also true for us, if R goes positive and negative on this interval, alpha to beta, you're screwed. You probably will get the wrong answer. So you have to be sure to pick an interval where either A, R is positive the whole time, or B, R is negative the whole time. You can't have R fluctuating between positive and negative. So you want, and I'll write this down, R to be all positive or all negative, one or the other, on the interval alpha to beta. If it flips back and forth, you got to shorten up your interval and work some symmetry or something like that to make it all work out. Okay. So we're not going to use this formula in Calc 3 because we don't need to, because our formula is better. So first I need you to remember, what is the integrand when you're using a double integral for area?
1.
1, very good. Yeah, very good. So that's still true. Good news. Well, what do you mean? You're going to still, so you're going to have a double integral. This is your area element, r drd theta. And your theta is still going to be from some angle alpha to some other angle beta, what have you. And then you're going to have your r be some function of theta, g1 theta, to another function, g2 of theta. Okay, fine. Now, if g1 of theta is just r equals 0, if it's 0, which is very common, in fact, it's very common, but not, not necessarily all the time, but for a lot of what we're going to be doing, then what's kind of cool that I want you to notice is that if you take the integral of the innermost integral, you're going to get r squared over 2, and then you'll have like 0 to g2 of theta, okay, and then d theta. And then what this is going to look like is it looks like 1/2 g2 of theta squared d theta, where theta goes from some alpha to beta. And this is the same business that you had in Calc 2. Same thing. And again, you want your g2 of theta to not be all positive and negative, all over the place for your interval. You want to choose something where it's all positive, all negative. Okay, so we're going to do one example and then call it. All right. So we're going to do something that you actually did in Calc 2, which is find the area of one petal of a flower, a rose petal. And do you like my meme? Pirate
Beautiful.
text messaging.
It's
R.
all right.
R.
All right. Yeah.
You get it? You guys aren't having any sense of humor today. Maybe because it's Monday and you took a quiz. You're upset. Okay. You give a peg leg for a dash of gums. Untreated scurvy. Well, Isaiah, because everything we do in this class is chickens. Have you not learned yet to love your chickens?
Is that a euphemism for something? Like,
Yeah.
what did I miss?
How the cluck do I do this? All right. So if you whip out your calculator again, and I'm afraid to do mine because my memory is going to die. You will get a cute, what they call a rose petal, and it's like 3 petals here. Okay. So you want to find the area of this flower. Now, why are they asking? So they're asking for the whole thing. Now, here's your problem. Do not try to find the area of the whole entire flower. Because you'll go, oh, area is, 0 to 2 pi, 0 to 3 cos 3 theta, already theta, and you'll probably end up getting 0. And you're going to go, oh, well, this area doesn't look like it's 0. What the heck happened? What did I do wrong? And what you did wrong is you mistakenly used this lovely double integral formula for area of a polar graph when r bounces back and forth between positive and a negative. If you graph 3 cos 3 theta on 0 to 2 pi, you're going to see it, going positive and negative. It's going to look something like, so what you need to do is you need to pick where it's either all positive or all negative. So I claim that we're going to use symmetry. The area is going to be equal to the total area 3 times the area of one petal, because there is symmetry here. And if we can just find the area of one petal and there's 3 petals here, we'll multiply by 3 and we'll be cool. And we won't end up getting weird numbers like 0. So how do you get 1 petal's worth? Well, this is the hard part where you're going to have to solve a trig equation. when this petal curve gets drawn out, it starts here at the pole and it goes, and then it crosses the pole again, then it crosses the pole again, then it crosses the pole again to make these other petals. So when does R equal 0? Because if you can find in one of the petals interval where just one of the petals is sketched out, you'll be safe. So when does R equal 0? This is a trig equation. This is to get your limits on theta. That's the question you're asking. So if you divide both sides by 3, you can kill off your 3. And then you take arc cosine of both sides of this equation. Does anybody know what arc cos of 0 is? Quick.
1.
It's going to be pi halves.
Nope.
Yeah, it's going to be pi halves. Now, there are other answers, so I'm going to put other answers. 3 pi halves is also a place where cosine goes to 0, and negative pi halves. All of these are good, you know. And so then on this side, after you take cos inverse of cos of 3 theta, you have 3 theta. And then what you do to solve for theta is you multiply both sides of this equation by 1/3, and you'll get theta will be like negative pi 6, positive pi 6, 3 pi 6, but reduces to pi halves and so on. So you want to pick one of these intervals. I'm going to pick negative pi 6 to positive pi 6. And I claim that if you graph using your graphing calculator in polar mode and you restrict your window to theta min being negative pi 6 up to theta max being positive pi 6, it'll sketch out this one petal over here, okay? And that's one that we want. So what I'm saying is our double integral over here, which is area, we're going to have negative pi 6 to positive pi 6 for our theta limits. And R is going from 0 to 3 sine, or excuse me, 3 cos, my bad. 3 cos, sorry, 3 cos, come on, baby. Come on, go back to non-erase mode, okay? Come on, it's okay, you can do it. Nope, it doesn't want to get out of erase mode. That's funny. Okay, how can I force it to get out of erase mode? I'll go over here and go, I want to draw, baby. I don't want to do any more erasing. Aha, there we go. And then you're going to go, okay, the area element is RD theta. And then you go ahead and you integrate. And then we are going to multiply this by 3 ultimately because we want the total area. And we'll multiply by 1 petal's worth. So you know the drill. The antiderivative here is r squared over 2. And when you're going to go to 0 to 3 cos 3 theta and then plug in your limits, you're going to, you're going to get 3 cos 3 theta squared over 2. And sorry for the mess. I'm writing in invisible ink right now. What is 3 cos 3 theta getting squared?
That's 9 cos.
It is symmetric from negative pi 6 to pi 6, Emily. No, you don't want to multiply by 6. Oh, please don't. God, no. No, because again, you're going to be in danger of going positive and negative, Emily. Please don't do that. No. No. So does anybody know what we're going to do now?
A reduction.
Yeah, you're going to have the integral here, 3 squared, that's 9. And then you're going to have halves. And then you're going to have cos squared of 3 theta. And you're going to need the power reduction formula. Okay? So the power reduction formula is going to be used here. Now here's the killer part. I'm going to purposely put an error in here. Play teacher on me and find the error. What is wrong with my power reduction formula for this problem? Does anybody see
Multiply
it?
the 3 by 2. So
Good.
it's 6 theta.
Good. Yeah. So you're gonna, this needs to be double. This argument should be what? 6 theta, yes? I'm not gonna do the rest because I'm really strapped for time. So what I'm gonna say is that this final answer, well, 1 petal's worth is 3 pi fourths. And then when you multiply by 3, your final answer is 9 pi fourths area for the whole entire flower. So what's the point of one of these problems? Well, it's similar to your Calc 2 days, so that's kind of a neat little connection that I'd like you to make. But we're using a double integral. And that caveat that you can't have r go positive and negative on the interval is still in effect. If you violate that, and that's what I was saying, Emily, why you can't do that multiply by 6 trick that you thought was going to work for you, is you need to maintain r being positive only or negative only in the interval. And if you restrict yourself to that, the area formula will work okay. All right, so there you go. And of course, power reduction formula. I love that. And you're going to see it again. Now let's do mass. I got time, I'm going to use it. So what about it? We're going to do mass of a planar lamina, which is just like a thin film. It's a 2D thing. Normally in a physics class, you probably find mass of solids. And we will find mass of solids also in this class at the end of the week, don't worry. But let's start with mass of a planar lamina. So we're now in a part of 16.6 right now. I'm just going to cover a portion of it. So how do you find the mass of a planar lamina? Well, what if your planar lamina, here's a planar lamina right here. Okay, there it is, that region R. What if it had a constant density? And we'll call the density rho. That's pretty typical of math textbooks. So lamina of constant density rho. What of it? Well, then the mass would equal your density times your area. Oh man, I'm all over the place. So mass, and this is a physics thing, is density times area. So for us, if density is a constant, then your mass would simply be rho times the double integral over your region dA, because you guys now know that a double integral can be used to find the area of a region, right?
Yeah.
Now,
yeah.
so that would work. Now, here's the thing though. Usually your density is not constant. Usually your density, we're not doing volume, David, we're doing area. When you have a double integral with a 1 as its integrand, David, that represents area. Only when you have a capping surface will you put the capping surface in your double integral, and that represents volume. Please know the difference. Okay, David? This represents area. This, and I'm talking to you, David, but I could be talking to the rest of the class. This represents a volume. Do you see the difference, David?
Yeah. It was just that,
Gotta know
you
it.
know, P is equal to M over V. That's all. P is equal
Okay.
to M over V. Jesus. Yeah.
We're not doing that right now because we're doing your rho is going to be some mass per area. That'll be the units for your rho. And it's going to be a density function. So let's say you have some sort of density function which is variable. So you've got rho, it's some continuous density function on some lamina. That's going to be a 2D thing corresponding to some plane region R. Then the mass M is going to be the double integral over your region, and you're going to put the rho into your integrand. So this looks like a volume double integral now. It looks like a volume double integral, but instead of putting your capping surface in that integrand, you're going to put the density function. That's the only difference. And the answer is still going to be positive. So let's do an example of finding a mass. We're going to use a double integral to do it. So let's say you have a triangular lamina and they're not giving you the equations, they're just giving you the point, 0, 0, 0, 3, and 2, 3. So here is your lamina right there. It's a little triangular region. And let's say your density is given by 2x plus y. That's variable. So your mass is going to be the double integral over the region, and you're going to put your mass, your density function into the integrand. Okay, now this is not polar. Okay, I know we've been doing a lot of polar, but please don't convert to polar here. That would be very bad of you to do. Why?
Nothing circular about
Yeah, there's nothing circular about this region of integration at all. You'll be in a world of hurt if you try converting this to polar. You're going to stay in rectangular, okay? Stay in rectangular mode and just go for it. Now, folks, you can either pick the x dy or dy dx as your order of integration. Both are fine. And I usually, oh, I have no reason why that came up. Usually I love dy dx. That's my personal favorite, but I'm going to be honest with you. This region where it's not flush with the x-axis, it's more flush with the y-axis. It's better if you choose dx dy. It'll be a little easier. If you don't believe me, go do it on your own. So if I choose the dx dy, and let's iterate the double integral, what's y doing on this integral? What pure number to what pure number is y doing on this cute little triangle?
0 to 3.
Good, 0 to 3. Now what's x doing? That's the trick. If you put a little man in here sideways, because he's got to be sideways. Oh, he's kind of squinched in there. His feet are going to be on the y-axis, which is x equals 0. But his head is going to be on this line. And so guess what? You have to use your algebra skills and figure out the line equation. Do you guys know how to do that if you're given 2 points? Please say yes, for God's sakes.
Slope.
Oh my goodness. So you have 2 points, the 0.00 and the 0.23, your slope, which is going to be change of y over change of x. Change of y is 3 minus 0. Change of x is 2 minus 0. I get 3 halves. And it looks like the y-intercept is 0. So y equals 3 halves x. But do I put 3 halves x up here, up top, for my limit?
No, you said it equal to x.
Yeah, good. Yeah, thank you. Do not do that because you're violating one of the rules of iterating integrals. You want to solve this for x and make x look like a function of y here. So that's how you're going to iterate this double integral. So now 2/3 y will be the upper limit. And then you'll go ahead and integrate with respect to x. You'll have x squared plus yx, and then you'll evaluate this between 0 and 2/3 y. And then that will give you what? 2/3 y squared plus y times 2/3 y. And then you'll integrate this with respect to y. But if I clean this up a little bit, this is 4/9 y squared plus 2/3 y squared. And I'm going to add like terms because that's doable. Those are both y squared terms. But what the heck is 4/9 plus 2/3? I believe it's 10/9. And this is pretty easy to integrate. I get y cubed over 3, and I'm going from 0 to 3. Final answer, 10. And that doesn't have any units because mass is unitless in the world of physics. Okay, I'm going to do one more problem because I can. And so please stay if you can, because this problem is going to be similar to a problem on your midterm. Yeah, I was looking over your midterm over the weekend, firming it up a little bit. So although your midterm, you're going to be asked for mass of a solid instead of mass of a lamina. So know how to do it all. So here you're being asked to find the mass of a lamina in the first quadrant. Okay. And so it's going to be a portion of a circle, but in the first quadrant only. So the lamina is going to be that guy there. This is the circle of radius 2 centered at the origin. So we only care about this first quadrant portion. And the density, they're not giving us the density function. Aha, this is the hard part. They're just telling us, oh, guess what? The density is proportional. It depends. It varies depending on how far the point is away from the origin. So like if you pick an arbitrary point here, x, y, and you go, oh, how far away is it from the origin? We'll call that d. And because it's proportional and you need a constant of proportionality, we'll call it k. That could be, some weird constant. So you don't know what that is, but that does have to be part of the answer. And then do you guys know how to use the distance formula between 2 points in 2 dimensions?
Yes. Mm-hmm.
I certainly hope so. So this is like a good exercise. So if you take the distance between x, y, and 0, 0, you should get x minus 0 squared. That's just x squared. Plus y minus 0 squared. That's just y squared. And so there's your density function. Okay, sweet. So what are we saying? We're saying the mass is going to be the double integral of this region. And then the density function goes here in the integrand. And then you're going to have some area element. Well, this is a perfect candidate for polar. And if I were you, I'd convert to polar. And we are. So, here's the deal. This region R, Here's your region R. R is going from 0 to 2. That's the radius. And then the limits for theta is 0 to pi halves because it's just the first quadrant. So you're going to go 0 to pi halves, 0 to 2. And then this density function is converted to polar. K times square root of x squared plus y squared is square root of r squared, which is just r. And then the area element, be a pirate, r dr d theta. And then don't forget to multiply your powers of r together to get a single power of r before you integrate. Otherwise, you'll end up in a world of hurt. And then I'm just going to say, et cetera, et cetera. This is a pretty easy problem to finish up because it's easy integration, nothing crazy. And it turns out the final answer, the mass is 4 pi k thirds. And that's the final answer for that problem. I'm done. Thanks for staying. Congratulations. You finished polar. You finished 16.6. On Wednesday, we're going to do two things. We're going to do 17.6, which is surface area. And then we're going to do 16.4, which is triple integrals. So I'll see you there. Bye.
Have a good one, Professor.
You too.
See you Wednesday.
See you Wednesday.
Or sorry, Avasti scurvy dogs.